Thank you. It's such a pleasure to be here and to introduce for you energy balance models. I'm going to do this introduction using a historical approach because some of the transitions were pretty remarkable and very interesting. When we talk about energy balance model, the way it's used today, what we mean is a thermodynamic model. That means a model that's based on the first law of thermodynamics and typically involves differential equations. However, the purpose of these models are to ultimately predict weight change. So predicting weight change is an important activity even if you don't have knowledge of thermodynamic models. So back in the early days, they did need formulas to predict weight change, and we'll start there. One of the most classical landmark studies in weight change is the Minnesota starvation experiment run by Ansel Keys. 32 young men were recruited to undergo severe caloric restriction for a 24-week period in residence at the University of Minnesota. And they were followed by a recovery period where they were refed. During the starvation period, Ansel Keys sought a model that predicted body mass at week T, M of T. And what he noticed was that the data, when he plotted it, formed a concave up curve. So he decided to assume that M of T was in the form of a concave up curve, which the most famous concave up curve that we learn about in calculus is a parabola or a quadratic equation. So he assumed that M of T took that form, and it became his job to just solve for the parameters A, B, and C dependent on that individual. He did this by assuming that the minimum of the curve occurred at 24 weeks, which was the length of his study. There are a number of ways you can use this information. I chose to take the derivative and plug in t equals 24 and set that equal to 0, forcing the a and the b to comply with the minimum being at 24 weeks. That gives me an equation where I can solve for b in terms of a. Two more pieces of information were available to Ansel Keys. One was that at time equals 0, he knew the baseline weight, that's M0, and he also knew the weight at 24 weeks, which kind of defeats the purpose of predicting what happens at 24 weeks, but he can plug in that piece of information into this formula, and he arrived at a final form of the formula that looked like this, where MF and M0 appear, and P is the desired percent body weight loss. So like I said, it's a calibration. It's not really a predictive model, but as you would expect, it calibrated pretty well. These are the average weights over time in the Minnesota starvation experiment, and you can see that Ansel Keys curve fits that data pretty snugly, as it should. So shortly after the Keys study, there was a remarkable study by Max Wishnowsky that kind of stuck in the dietary and nutrition literature, and that is Wishnowsky's 3,500 calorie rule. And I'm going to first show you that this rule, despite advances in modeling and sophistication and accuracy, is still being used today. This is a recent article in the Journal of the American Medical Association, which talks about healthy weight loss, and I've boxed off down here the citation towards the 3,500 calorie rule, which states that a total of 3,500 calories equals 1 pound of body weight. And Guth goes forward to state that more clearly that if you decrease or increase your intake by 500 calories a day, you should expect to lose or gain 1 pound a week. So this model is a linear model, and it was the first development that connected energy intake to weight gain or loss. The landmark paper that discusses this 3,500 calorie rule was published in 1952, and it drew upon some of the conclusions made in the Minnesota starvation experiment. Max Wishnowsky took the best available data at the time, which included short-term studies which in women, largely women, that were obese and were placed on a very restrictive caloric diet. And in this short-term, mostly female study, he came to the conclusion that 1 pound of body weight lost is approximately 3,500 calories. So that's where it came from. So it's important to understand that this is a different talk, but that statistical models usually do best on the population they were developed for. Unfortunately, the issue that we have is that this model is being used and extrapolated to cases it wasn't developed for, and it's not doing well on those other cases. David Allison, Steve Heimsfield, and myself wrote a letter arguing that thermodynamic models, which I'm going to end the talk with, should be used in place of the 3,500 calorie rule. And we're going to come shortly to the first thermodynamic model, which questions exactly this linear form of predicting weight loss. If you want to look at this as a model, you see that body weight here in pounds per on time is in days, can be predicted by plugging in the initial weight, subtracting the calorie deficit. In the case of the Guth paper, this is 500 calories, and T is the number of days of weight loss, and 3,500 is the 1 over 3,500 is the slope. So you can plot this in Excel. Take an initial weight of 250 pounds, and you see that this individual's weight loss curve, in this case, would be depicted by this line according to 3,500. There was a gap in predicting weight loss for about 20 years, and on the weight loss scene comes an incredible investigator, Gilbert Forbes. Gilbert Forbes was a pediatrician, and I say incredible because he had a feeling for mathematics that we wish that our students had but never seemed to achieve. He had an uncanny understanding of what mathematics was and what calculus was, and if it was a different era, I believe he could have derived calculus on his own. So what he did is he looked at, he did a number of things, but what he did here was look at starvation studies and weight loss and starvation studies. He was interested in predicting weight loss during complete fast. What he noticed was the curves are concave up, but he went further than that. He said there looks like there's a rapid decline at the beginning, followed by a plateau. And I know the kinds of models that do this. The kinds of models that do this are dose response curves. But since I have this really rapid phase, it's probably a sum of two dose response curves. He has conjectured here the solution to a second order linear equation, a differential equation. And in fact, I put those lambdas there. He, I think, uses F1 and F2, but I use lambdas there because in mathematics and engineering and physics, we typically represent an eigenvalue by lambdas. These are the eigenvalues of a second order linear differential equation. So without the training, he's conjectured this, which is pretty amazing. He fit what we would do if we had the second order linear equation is we would solve for the eigenvalues and represent the solution like this as a spectral decomposition. What he did is he guessed that this was the formula. Wow, he just guessed out of the air that this was the formula. And then he calibrated the lambdas to actual data of weight loss data. And then he tested it on a separate testing set. So he used training data and then testing data with very good agreement, which is not a surprise when I show you some of the differential equation results. So he was also ahead of his time. But probably the loudest voice that was really ahead of his time was Vincent Antonetti, who was the first person to apply the first law of thermodynamics. In a different talk and a different workshop, I'm going to talk a little bit about the first law of thermodynamics and where it came from and what is meant by a law. But here in this talk, we're going to accept it. Rudolf Clausius was attributed to the statement of the first law of thermodynamics the way we use it in nutrition. In his mechanical theory of heat, he says in a thermodynamic process involving a closed system, the increment in the internal energy is equal to the difference between the heat accumulated by the system and the work done by it. That may sound confusing, but it really, in formulaic form to humans, breaks down to this. The rate of energy stored or lost on our body is equal to the rate of energy intake minus the rate of energy expenditures, all measured in an energy measurement per day, so calories per day or joules per day. So simple as that. You might have heard of this as referred to as calories in minus calories out. So I actually asked Vincent Antonetti, I had the pleasure of actually asking him, how did you decide to use the first law of thermodynamics to model back in 1973? Obesity wasn't really the problem we have today. Weight loss was not really the problem we had today. So what made you think of doing this? I mean, I was number 30 on the chain of people who developed a model based on the first law of thermodynamics. What made you be the first? So he told me a wonderful story. He was working at IBM in 1968, 1 year before I was born, and he had a number of engineering degrees, all with a specialty in heat transfer, thermodynamics, and fluid mechanics. And he was at a cocktail party, and he overheard two women who, according to him, were not very keen on him joining their conversation, but they were talking about weight loss. And he believes they were talking about Weight Watchers, and they stated, on this Weight Watchers program, you lose 2 pounds per week. So he had a couple questions. Everyone loses 2 pounds per week, no matter who they are. So if it was a man or a woman or a 130-pound woman or a 260-pound woman, they would all lose 2 pounds per week on the same calorie deficit. And if so, how long do they continue to lose these 2 pounds per week? Forever? Yes, they said, for as long as you're on the diet. And please go away. You don't know what you're talking about. You're an engineer. He was curious. So he went back and did a quick literature search. He wants you to know that there was no internet at the time, but still, and he didn't have access to a medical library, but still he couldn't find anything on the first law of thermodynamics applied to a mathematical model to predict weight change. He did find arguments, which are still there today, whether weight change was indeed governed by the first law of thermodynamics, and some people believe it's not, but there was no concrete model. Again, I want to say how ahead of his time he was. He recognized the fact that we work in disciplinary silos and that we don't really interact, and that if someone had an MD and specialized in treating patients, they may not have the time, energy, or knowledge base to go develop a thermodynamic model, whereas he, an IBM engineer, probably wouldn't have the insight to go and jump over to their field and start developing models. Lucky for us, he did, because he decided to look into the problem, and those are his words. So in 1973, to my knowledge, the first thermodynamic energy balance model was developed by Vincent Antonetti in a publication in the American Journal of Clinical Nutrition. I'm going to develop this model for you to give you an idea of how this is done. And then Kevin Hall is going to speak right after me, giving you more ideas of applications of a model and more complexities that can be introduced into this type of a model. But this will give you a good flavor for how these models are first developed. So we start with the energy balance equation. The rate of energy stored in calories per day is equal to the rate of energy intake in calories per day minus the rate of energy expenditures in calories per day. So what he did is he said, look, how does my body store energy? My body stores energy as my weight, my body weight. Body weight changes in kilograms per day. These are the effects of my weight loss program that I see when I step on the scale. I'm losing kilograms per day of body weight. But that's not the right set of units. I need to transform those kilograms into energy. And so he multiplied by the energy density of 1 kilogram of body mass. And he used exactly Wyszynowski's formulation that this energy density would be 3,500 calories per pound, which when you convert to kilograms turns out to be 7,700. Energy expenditures in each of the models that are going to be talked about here, energy expenditures is really how people decide to cut up the pie. So the way Antonetti cut up the pie is into 3 pieces. The 3 parts of rest are at total energy expenditure, where your energy goes out is the largest part is the resting metabolic rate, which accounts for almost 2/3 of the pie on average. I'm going to talk more about how that RMR piece is developed. The AEE is activity energy expenditures. It's what most people think about when they think about energy expenditures: running and swimming and climbing the stairs and playing with your hair. All of that is glommed into this one piece called AEE. Then there's actually energy expended by just digesting your food, which can be up to 5% of the pie. It's not a very large part of the pie. So you're not going to lose weight by eating more. The biggest part of that pie is resting energy expenditures or resting metabolic rate or basal metabolic rate. There's a number of very similar names and similar metrics. And we actually define this in a paper, and I quote the paper: RAE is usually taken as a subject's endogenous metabolic activity separate from the metabolic effects of food and activity. You can think of it as just the energy required to sustain your life, to run your internal organs. What's nice is that we can measure RMR. And so RMR has been measured since the early 19, or even earlier than that. Stephen Heimsfield is talking about this. And so we know how to calculate oxygen consumption. This is an example of a metabolic cart where most of the RMR studies are conducted, where there's a hood placed on the patient and you can record the oxygen consumption from there and convert that to energy burned. I've done a lot of fiddling with RMR models over the years. If you come into this area as a quantitative researcher, you can't help it. So I've looked at a number of different models that predict RMR based off of individual inputs like age, height, gender, and baseline weight. And they come about the same. I'm not even sure what this was that I was testing, which one of the models it was. This is an example of an RMR model against actual data. The data was collected at Kiel University in Germany, and you can see that there's very good correlation between actual and predicted. However, R-square in these cases are lower. So this is an independent testing of the model. The Kiel data would be a training set, and you see that the R-square explains about 70% of the variance. So there is some of the variance that's not explained by these initial inputs. So let's go back to Antonetti, that squared off piece. How is he going to deal with those remaining pieces? Well, RMR has been modeled by, I told you, a number of different models. At the time, he chose a model that was a proportion of body surface area because it has to do with, it's a surface model. And this was an existing model developed by Dubois. And you see here this A2, this coefficient, body mass to the 0.425 power. A2 is actually a function of age, gender, and height. So just like these other models that are functions of age, gender, and height, it's in here too. It's just encompassed inside a parameter. And these values came from a book by Dubois on basal metabolism in health and disease. So that RMR is now disposed of. AEE, Antonetti assumed, was a direct proportion of body mass, which is the same assumption that our team used and the same assumption that Hall's team used to develop their activity piece. Thermic effect of food is modeled by a direct proportion of energy intake. The more you eat, the more you burn to eat that food. But remember, it's only a small piece of the pie. Remarkably, this 0.10 that he uses as his proportionality constant was used by Westerterp in 1995. It's used by many others. So he was dead on for a number of these constants and a number of these developed terms. In the Antonetti paper, he first looks at Wisnowski's rule, and a number of you in this room have seen this picture developed by myself for a New England Journal paper and by Kevin Hall, but Antonetti beat us by several decades. He has shown here that the curve by the thermodynamic model is pulling away from the 3,500 calorie rule, showing a very rapid decline in 3,500, which is not observed in the thermodynamic model. Well, how do we know which one is right? Well, he validated his model against the Minnesota starvation experiment. A number of us have validated against Minnesota starvation as well, but he was the first. In 1973, he tested his model against the Minnesota starvation experiment, and you see very good agreement between model predictions and actual data. Antonetti also recognized that people don't maybe want or enjoy looking at complicated differential equation models. And at the time, there were no desktop computers. They couldn't program it. In fact, he programmed the model using punch cards. And it's incredible to me, he was using a precursor to Fortran 77. So he was using punch cards. These were the size of the computers back then. What he did is he ran the simulations and then he published them into tables into this book. So instead of typing in your initial data and then hitting go and seeing the simulation, you would flip through the book and find your table and it would give you the prediction. So this is just the beginning. Since that time of Antonetti's model, there's been 30 or so models developed. We seem to see new ones still appearing. And you wonder, well, how far have we come with the advances in biology that we know about weight loss? Well, not that far. Antonetti's model is not that shabby, and it compares very well to predictions between our model and Hall's model to different weight loss interventions. This is a validation of the three models against George Bray's study, which was held on a metabolic ward. It was an overfeeding study, and you see very good agreement between all three models, predicted and actual 57-day weight. Similarly, we see very good agreement between predicted and actual weight and weight loss studies. This is a study run by the Pennington Biomedical Research Center on caloric restriction, and you see Antonetti, Hall, and Thomas, our three models, do very well on the data. So Antonetti's model, developed back in 1973, does pretty well as a prediction. I told you there was a number of other models. I'll just give you a little summary, but there's many more than this. Klaas Westerterp, who's an energy expenditure expert in the Netherlands, has developed a model on, it's a dynamic model based on the first law of thermodynamics. It has some body composition model in there that's a little bit difficult to program, but not impossible. An astronomer by the name of Alpert developed in 1979 a two-compartment model, second order equations. So you recall Forbes's insight with the two terms. So Alpert is providing the differential equation for it. But I believe there's something not quite right in one of his models. So there's something circular that Carson Chow was telling me about. I haven't looked at that deeply. Kosciuszko is a mathematician, a card-carrying mathematician in a math department with a very heavy teaching load. And he's developed some very nice mathematical models that rely on Kleiber's law, which you're going to hear about here. So that model uses Kleiber's law actually for their RMR piece. J.P. Flatt has also a two-dimensional model, and his model is different than other models because he uses carbohydrates and fat as his two compartments. Unlike Antonetti, we have at our fingertips today smartphones and apps that are on the web. So this is our app, which has been recently programmed using Google. And so you can access this on the Pennington Biomedical Research Center website, along with a number of other calculators. Kevin Hall has a nice calculator on his website. He's going to be talking about that in his talk. So you can access any of this from anywhere. And our models have been programmed into every smartphone. And Corby Martin will be talking about that. So stop for questions.